Welcome back. In the previous lecture, we discussed the single phase diode rectifier with the resistive load. In this lecture, we will focus on the single phase diode rectifier with the inductive load. So the load that will be connected in the network is basically an inductor denoted by L. So the input voltage whatever we give is basically the single phase, given by the equation Vs is equal to Vm sin omega t. Again, this voltage is coming from the step down transformer with a ratio 1:n, and this is the secondary side of the transformer which is having the voltage Vm sin omega t. A diode is basically connected with the help of a switch. The use of a switch is to disconnect the circuit from the source. Once the switch is closed, assuming that the diode is ideal, the voltage whatever we give at the source will appear across the load. The average output voltage of the load is given by V0, and the current which is flowing in the circuit is I0, and the diode voltage is V0. So if we plot the waveform with respect to omega t, the source voltage is basically sinusoidal in nature with the equation Vm sin omega t. It means its maximum magnitude is basically Vm. The output voltage V0 with respect to omega t is same as that of Vs with maximum magnitude Vm, and in negative we have minus Vm, but the current which is flowing in the network will be equal to 2Vm by XL. So what we have is basically the voltage 2Vm, the twice the maximum voltage divided by XL. XL is the inductive reactance which is equal to omega into L. Omega here is the frequency given by 2 pi f. So Imax is the maximum current in the circuit. Now when the switch is closed at omega t equal to 0, the diode will start conducting, and if you apply the KVL equation in the circuit, so the source voltage will be equal to the voltage of the load which is V0. This is given by L di by dt, and I0 is basically the average current which is equal to Vm sin omega t. So this is the first equation coming from the KVL circuit. Now if we try to find the solution for the current I0 from this equation, so we have Vm by L which is a constant integrating sin omega t dt. So we have the solution minus Vm by omega L cos omega t plus some constant A. This constant A can be evaluated at omega t equal to 0. We know that the current is equal to 0, so we can put that and find what is the constant A. The constant A is nothing but Vm by omega L. Now if we substitute the constant A in the equation of the current, so we have the equation minus Vm by omega L 1 minus cos omega t, because this constant A will be substituted with respect to Vm by omega L, and hence we will get the solution for the average current of I0. The output voltage we can get V0 is equal to L di naught by dt. So if we differentiate the current whatever we got in the previous expression, we got the voltage which is nothing but the source voltage Vm sin omega t. Note down that the average value of the output voltage will be 0. It is because of the inductor, because inductor will store the energy in one half cycle and release the energy in another half cycle. So the average value will be 0. The output current I0 consists of DC component and the fundamental frequency component of the frequency omega. This is with respect to the ripples which is present in the network. So we have some fundamental component as well as the DC component. The maximum current Imax, that is at the load, occurs at omega t equal to pi, and if you find the maximum current Imax in the I0 equation, we got it 2 Vm by omega L. This is when we substitute omega t is equal to pi. And if we calculate the average value of the current, we can calculate it easily with respect to integration of the current 1 by 2 pi, integrating from 0 to 2 pi, because this is one full cycle of the AC wave which give you half of Imax as the equation on integrating it. So it means that whatever the maximum current we have which is occurring at omega t equal to pi, the average value of the current will be equal to half of that I max. However, the average voltage will be 0. So this has to be noted that average voltage is 0, but average current is not 0. Average current is half of the maximum current. RMS value of the fundamental current, if we want to calculate, so we know that RMS current is nothing but 1 by T, that is the time period. We give the integration 0 to T, and then we have the Vs square into dt. So this is the equation of the RMS. So if we substitute the time period as 2 pi and integrate from 0 to 2 pi, the equation of the voltage, and half indicate the square root, we get I naught by root 2 as the fundamental component of the RMS current. The RMS value of the rectified current will have the DC current as well as the RMS current fundamental component. So this is the average current I naught square plus the RMS first fundamental component of the RMS current half. So that gives us 1.225 I naught. So this is the RMS value of the net rectified current. This is RMS current of the fundamental current. The voltage across the diode will be 0 because diode is turned on in the network and there is no potential across the diode. It is in the on state. However, when we put the capacitive load instead of the inductor, what happens? The source voltage remains the same, the diode remains the same, the switch remains the same. So we give the sinusoidal voltage with the maximum magnitude Vm, and if you plot the output voltage, that is the capacitive voltage, the output current and the diode voltage, we will get this type of waveform. How do we get it? Let us do the analysis. So when the switch is closed at omega t equal to 0, we can get the equation of I naught as C dV by dt, and this is the source voltage Vs, which we can write as Vs sin omega t. So it means that current whatever we are getting is omega C Vm cos omega t. Output voltage V0 is again equal to the source voltage Vs equal to the capacitor voltage Vc is equal to Vm sin omega t. So once the diode is turned on, the whatever the source voltage we are giving Vs, the entire voltage is coming across the capacitor Vc. The capacitor is charged to a voltage Vm at omega t equal to pi by 2. It means at pi by 2, the net capacitor is charged to a voltage of the maximum value, and subsequently this voltage remain constant at Vm. So if we see the waveform here, you will see that at pi by 2, here at pi by 2, the voltage remains constant and it is at Vm. So we have at pi by 2, the capacitor voltage will be constant. Capacitor current or load current is maximum at omega t equal to 0 and its value is omega c Vm. So if we see again this waveform here, the current is maximum, its magnitude is omega into c into Vm. That is what we have the maximum current. The diode conducts for pi by 2 omega for omega t equal to 0 to omega t equal to pi by 2, and in this interval diode voltage will be 0 because diode is at on state. So diode voltage will be 0 and it will conduct from 0 to pi by 2. At omega t pi by 2, what happened? The diode voltage is given by, so diode voltage, if you apply the KVL equation, so diode voltage is equal to minus V0 plus Vs, where Vs is the source voltage and V0 is the output voltage with proper sign. And if we put the equation Vs is equal to Vm sin omega t and V0 at pi by 2, we have the maximum value Vm. So we get V sin omega t minus 1. So this is the equation of the diode voltage at pi by 2, and that is the time origin we have to redefine at omega t equal to pi by 2. So from 0 to pi by 2, we have again this pi by 2 will be considered as 0 because the time origin will be refined and we will be getting the equation. So let us see again the waveform. This is the diode voltage. So diode voltage at pi by 2, if we see it, it is totally on state, and then we have at the negative range. So this is the diode voltage. So diode voltage, whatever we discuss, is V sin omega t minus 1, and omega t equal to pi by 2. After that, the diode voltage is obtained, and at omega 2 3 pi by 2 Vd is equal to minus 2 Vm. So in this way we get the waveform of the diode voltage. if we compute the average value of the voltage across the diode Vd, which is again integrating from 0 to 2 pi, so we get it is equal to root 2 Vs, because this is the equation of the voltage Vm sine omega t minus 1, which we saw in the previous derivation. So here we have the equation root 2 Vs. Now note down here that is equal to Vm only. So whatever the Vm value of the source we got it, that is equal to root 2 times Vs is equal to Vd. RMS value of the fundamental component of voltage across diode, if you want to find out, then we get it Vm by root 2. This is again the equation of the RMS current, half indicate the square root, and square term will be appearing in the equation, and we will integrate from 0 to 2 pi. So it is equal to Vm by root 2. And RMS value of the voltage across the diode will be under root of Vd square plus the RMS current, whatever we have for the fundamental component. So this is equal to 1.225 into Vm. This is the RMS value of the voltage across the diode. So both the fundamental component as well as the DC component will be present. And in this way, we have discussed three important load configuration, that is the resistive load in lecture number 3b, and in this lecture we have discussed the inductive load and the capacitive load 3c. In the coming lecture 3d and so on, we will discuss the other type of loads like the combination of RL load, and you can have RLE, that is the source, as well as the freewheeling diode. What is the role of the freewheeling diode in the circuit? So thank you for now. See you in the next lecture.